All right, back for segment 3 for chapter 2. We're just starting chemical equations, and so of course we use chemical symbols and formulas to represent reactants and products. And so we know that the reactants then are on the left side, the products are always on the right side. There's always an arrow in between that typically means reacts to yield. We'll also say produces, makes, things along those lines. An example reaction we were looking at was methane, CH4, burning in oxygen, so plus CO2, plus O2, is going to produce or reacts to yield CO2 and water. The coefficients in this case are the numbers in front of the formulas. So for instance, we have a 2 in front of the O2, that's a coefficient. Remember, the little 2 here is a subscript. Subscripts tell me what's connected together. Coefficients are telling us what is actually there, right? So it's indicating how many of each type of molecule reacted or formed, okay? Now, when I go to read the reaction, I would say methane reacts with oxygen to produce or reacts to yield CO2 and water. Notice I don't say the coefficients when we say the sentence, right? So hopefully remember that every sentence is a skeleton equation. And then once we have the skeleton equation, we would be able to balance the equation. So we'd end up with a balancing of the equation. Now the reason why we balance is the conservation of mass, right? And we know that mass cannot be created nor destroyed. So this means that we have to have the same number of atoms on each side. Now obviously the connection is what's changing, not the number of atoms. So as long as we have the same before as after, we call that a balanced chemical equation. And so here we show the methane, CH4, here's the CH4 reacting with the two O2s to form CO2 and the two waters. And so here we can see we have one carbon, 2, 4 oxygen, 2, 3, 4 oxygen. We had 4 hydrogen here. We now have 2 plus 2 hydrogen there. So if you want, you can write it out that way, and you can see that it's going to work out. And of course, we call that a balanced chemical equation. All right, so here's another balanced chemical equation. This is going to be butane reacting with oxygen, also to form CO2 and H2O. That's a very common reaction. You may recall that that's combustion, and combustion, if it's complete combustion, always gives us CO2 and water. We could also have incomplete combustion, and incomplete combustion would be CO, so carbon monoxide and water. All right, so our subscripts, they're going to define the identity of the substances. That's the ones in blue on the reactant side. We have the C4H10, the O2. Red on the product side, we have the CO2, H2O. Now, these must not change when the equation is balanced. So once we've agreed that we're taking methane, or in this case butane, and reacting it, then we can't touch those subscripts ever again, because if we do, then we're actually describing something completely different. So that means for this butane, you're always going to get 4 carbons and 10 hydrogens per molecule, and we're stuck with that molecule now. For the oxygen, we have 2 oxygen per molecule, and then for our products, the CO2, we're going to have 1 carbon and 2 oxygen, and then for the water, we have 2 hydrogen and 1 oxygen. All right. Now, to balance it, we have the 2, 13, the 8, and the 10. These are our coefficients, right? These are indicating how many of each one of those molecules we needed. Now, these are the numbers we can change. So we adjust the coefficients to balance the whole thing, right? And so now we're saying we have 2 molecules of this react with 13 molecules of that to produce 8 molecules of CO2 and 10 molecules of water. All right, so how do you determine if an equation is already balanced? Well, you literally just count the atoms, right? Again, you have to have the same number of each type of atom on both sides of the equation. And so if you say yes to that, then it's balanced. And if you say no, then it's unbalanced. And that means we have to balance it. So the reactants and the products then, what we would do is say, okay, we have 2 times 4 carbons gives us 8 carbons and 8 carbons. 2 times 10 gives us 20 hydrogens. 10 times 2, 20 hydrogens. 13 times 2, 26 oxygen. Now the oxygen on the product side breaks down a little differently. So here we have 8 times 2, right, because we have 8 CO2s. And then we have 10 times 1 because we have 10 waters, each with 1. All right, so learning check. Let's take iron 3 hydroxide, react it with HNO3, and we're going to produce iron 3 nitrate and water. So we have our reactants and we have our products. So the first thing we'll do is look at our iron. On the iron, we have 1 on the reactant side, 1 on the product side. For oxygen, we have 3 coming from the FeOH3 plus 2 times 3, which gives us a total of 9 for the reactant side. On the product side, we have 3 times 3 coming from the nitrate, and then 2 coming from the water for a total of 11. So already we can see there's a discrepancy. Next, we look at the hydrogen. We have 3 in the iron 3 hydroxide. We have 2 of them for the HNO3 because we have 2 of those. That's a total of 5. And then we have 2 times 2, so 2 waters with 2 hydrogens each gives us 4. And then last but not least is the nitrogen. We have 2 nitrogens on the reactant side and 3 nitrogens on the product side. Now that's obviously not balanced. So only the iron has the same number of atoms on either side, right? So how can we fix that? And that's what we're going to look at next, right? We need to be able to balance. So I'm going to add to this slide a little bit. Now, if I want to balance this, what are we going to do to balance it? So the irons don't match. The irons do match up. The oxygens do not. So it looks like we need 2 more oxygens on the product side. So what would we do? Well, we could put a 2 in front of this one. That would give us a bunch of extra oxygen. We could just change this. That might be our best bet, is just to get rid of this coefficient right here and get rid of that coefficient right there. I don't like that they left it this way. All right, so we would just change this up. So let's go back just a smidge here. So for iron, I'm just going to put them in the middle. And then we have oxygen, and then we have hydrogen. Now one thing we could do is cheat a little bit. And what I mean by that is start noticing different things. So here's nitrates. That didn't break apart and that didn't break apart. And here's hydroxides. So we're starting to list this off as 4 different things. That might be a little on the tough side. But over here, if I look at water, remember we can write water as H. And then I can put the OH in parentheses over here. So now I can start to look at things as moving as units. So I have the OH here is the same OH there. Well, over here I have 3 of them. So I'm just going to throw a 3 in front of this water right off the bat. That's going to give me 3 OHs there. Here I have 1 NO3, but I need 3 there, so I'm going to throw a 3 right here. And that's going to give me 3 NO3s and 3 NO3s. So my NO3s and my OHs are now balanced. What about my irons? Well, I didn't touch iron, 1 and 1. And how about hydrogen? Here I have 3 hydrogens, and here I have 3 hydrogens. So a quick little trick there is to use those polyatomics. And if the polyatomic does not break apart, then you can balance them as units, right? It was bugging me that they left it that way, so we had to do that, sorry. All right, so your turn. How many atoms of each element appear on each side of the arrow in the following equation? So, reactants and products. I'll give a pause here, so that way you can write it all out, then push play and see how you did. All right, so for nitrogen, we had 4 times 1, which gave us 4, and then 2 times 2 on the product side, that gave us 4. For the oxygen, we have 3 times 2, that's going to give us 6. And then over here, for oxygen, we have 6 times 1. That also gave us 6. For hydrogen, we have 4, right? So the coefficient 4 times 3 gives us 12. And then over here, we have 6 times 2 gives us 12. So everything worked out to be 4, 6, and 12. Hopefully that worked out for you as well. All right. Count the number of atoms of each element. So again, it's another your turn problem. So I'll give you a chance to pause here. And now we'll check your answers and see how you did. Hopefully that all worked out for you. All right, so if you're struggling to figure out how many atoms are in each one of these, make sure you get up with me. Again, I'm under the impression that this is kind of like old stuff for us, and that figuring out how many atoms of each type are there is not a big deal for you all. In fact, I wouldn't be surprised if most of you could balance already, but we won't see balancing, I think, until the next chapter. But I just couldn't let that one reaction go. Sorry. All right, so ions and ionic compounds. So ions, we transfer one or more of our electrons from one atom to another. So we can either lose electrons or we can gain electrons. It's only our electrons that are going to move, right? So we're going to form electrically charged particles. That's going to be our ions. Now, for our ionic compound, it's basically just going to be a compound that's composed of those ions. So we're going to form our ions from metals and nonmetals, right? And once we do that, then we're going to form an infinite array. So in other words, just a pattern, an organized pattern of plus and minus charges. So an infinite array of alternating plus and minus charges. Now, our metals are always going to form our cations, and our nonmetals are always going to form our anions. Okay? And when we do that, we'll form our formula units. So our pluses and our minuses will attract one another, and that will give us our smallest neutral unit for our ionic compound. So most of us are familiar with table salt, sodium chloride. Here we're telling you that sodium and chloride will make an infinite array. So they'll arrange themselves so that sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine. And basically, if I think of that as a big net, and I take one of those sodiums, it'll be surrounded by how many chlorines? Well, if I was going to draw that out, so I'd have sodium in the middle, and that's going to be surrounded by chlorines. So usually seeing these chlorines are easy. 1, 2. Now, sometimes these are easy to see. We're going to have one on the bottom and one on the top. And so at this point, we'd say 4. We have 4 chlorines around the sodium, but don't forget, we have a 3D world. So coming in and out of the board like that, we'd have a chlorine here and a chlorine here. I shouldn't say chlorine, chloride, chloride. Now, the other piece to this, remember it says an infinite array, and our formula needs to be 1 to 1. So in the gap here, I'd have all these chlorines. Well, over here, I'm going to have another sodium. And this becomes part of the array. So I have this chlorine attracted to that sodium, as well as this one. Now, I'm hesitant to draw bonds here. I don't want you to think of them as bonds. Okay, but they are bonds, but they're not bonds like we think of bonds when we're looking at balls and sticks, right? So that's not how it works for ionic compounds. For ionic compounds, it's literally the attraction of these charges. We have a plus charge over here and a minus charge over here. If we think of them as spheres, then we're going to have as many negatives that can get near that positive as that they can, right? And that's going to be 6 in this case because it's 1 to 1 for the charge ratio. Now, I don't want to write out Na infinity, Cl infinity, right? That would be insane. So what we do is we boil it down to the lowest whole number ratio. So for sodium chloride, it's 1 to 1, right? Hopefully that made some sense. All right, so what's going on when we form that ionic compound? Well, we have our metal, our sodium, our nonmetals, our chlorine, and we're going to make this ionic compound. So what happens is sodium is willing to get rid of an electron, and so it's going to get rid of its electron, and chlorine really wants the electron, so it takes the electron. Once that happens, we make Na plus and Cl minus. They now have opposite charges, and that's what's going to lead to the attractive forces. So in ionic compounds then, we're going to have our cation, which is our positively charged ion. And again, these are formed mainly from metals, only from metals really, with just a few exceptions for our polyatomics. The atoms lose their electrons. That's how they're going to make the positive charge. So we have protons, neutrons, and electrons. Only the electrons can move. The protons and the neutrons, they're trapped in the nucleus. They can't get out. So they're fixed numbers. The electrons are on the outside of that whole sphere, and so it can move in and out. And in this case, we're going to move out. Those electrons are going to move out, and they're going to form positive ions. So sodium has 11 electrons and 11 protons to start off. Once it loses an electron, it now has 10 electrons, and that's how we get the +1 charge. Now for anions, it's just the opposite, right? We have negatively charged ions, which means we're going to be gaining electrons, and it's only going to be the nonmetals that gain the electrons. Chlorine is going to have 17 electrons and 17 protons, but if chlorine accepts just one electron, then it becomes 18 electrons, 17 protons, and now we have a -1 charge. Hopefully that's all resonating with you. Now, experimental evidence for ions. If I take solid sodium chloride and I put it in between this battery, we get nothing, no light bulb at all. If I melt the sodium chloride so that it's a liquid, all of a sudden we have electricity going on. If I put pure water in, no electricity. If I put salt in the water, we get electricity, we get a light bulb. So electrical conductivity requires charge movement, right? So the only way we can get electrical conductivity is to have the movement of charges. So in an ionic compound, we do not conduct electricity in the solid state. The electrons have been transferred and they're locked in. They do conduct electricity in liquid and aqueous states where ions are free to move about the building, right? So as long as they're able to move around, then those charges can transfer back and forth. For molecular compounds, no matter what physical state they're in, they are not going to conduct electricity. They are insulators, right? So remember, molecular compounds are typically going to be insulators. Now I say typically because in today's scientific world, you can always find exceptions to everything. In fact, people have taken time to design molecules that can pass charges, right? But if you pull that out and you look at just the general science, the general chem, then we would say that they are insulators. Okay, so molecules are comprised of uncharged particles and will act as insulators. Now your ions for your representative elements. So here we got it basically broken down like the periodic table, 1A through 7A, and you can see that all of group 1A is going to be a +1, and all of group 2A is going to be a +2. Aluminum is the only one in group 3A that's a guaranteed +3. It's the only one guaranteed. So gallium does have a +3, but it's got other options. Okay, and we'll talk about that a little later. For 4A, we typically think of carbon as going to be a -4 and silicon as a -4. Right now, once we get into organic chemistry, you're going to see that that charge on the carbon and the silicon, it's a funny fickle thing, and there's going to be different models that are going to show it as a +4 and as a -4. Same with silicon, +4, -4. It just really depends on the situation, and has a lot to do with electronegativities. There's a lot of little details that we haven't discussed yet, as well as bonding and connectivity and structure. So once we get into some of those things, we'll start to look at some of the exceptions. And in fact, a lot of times I'll point out the exception and ask you your thoughts on it. And how is it an exception and why? Or how can we make sense of that? Or how is it stable this way? For 5A, we see that nitrogen and phosphorus are both -3s. Now phosphorus, and this is one of the big things we're going to learn in bonding this year, we're going to again be able to do some hypervalency there. So we're going to introduce the d orbitals, and once we have those d orbitals, phosphorus can play a little bit different of a game than the nitrogen. Now the nitrogen is pretty much fixed. If it's going to be an ion, it's going to be a -3. Now its oxidation number, which is a little different, we're going to find out can do some strange things, right? But it can't straight up be a +5 ion. That doesn't happen. Now for 6A, typically -2, -2, -2, -2. Not a whole lot of exceptions there. Again, we'll see once we have that d orbital. We can play some other games for the sulfur and the selenide. We don't really talk about beryllium much at all. 7A, you have the halogens, pretty much typically -1. Now I've already pointed out that down in this area, and again because of hypervalency, the bromine and the iodine, along with these noble gases that are down here, they can also do some funny things for bonding. And we'll look at some of those exceptions. In fact, that's what a lot of people don't like about chemistry, is we have exceptions to all of our rules. And we actually have rules for exceptions about exceptions for rules. So it gets a little complex. I understand that. It just takes time and kind of mentally gymnastically working through. All right. So we can basically use our periodic table then to predict the charges of our ions. When we use the North American numbering system, which means we have the group 1A, the charge typically lines up with the group numbers. So 1A is +1, 2A is +2, so forth. Until you get to the 4A. 4A is when it switches, and then we have -3, -2, -1, and then we actually call the noble gases the zero group. So All right, let's look at ions of representative elements. Noble gases are especially stable. So nonmetals, we have the negative charge on the anion, number of spaces you move to the right to get the noble gas. So expected charge on oxygen, move 2 spaces to the right, and so you get -2. What is expected for nitrogen then? Well, now you're going to move 3 spaces, and so you should get a -3, right? Rules for writing your ionic formulas: the cation is always given first. So we always write the metals first. We always want to tell you the positives before we start to explain the negatives. The subscripts in the formula must produce electrically neutral formula units. So you can use a charge balance ratio if you want. If sodium is a +1, oxygen's a -2, then I'm going to need 2 sodiums to balance that oxygen, right? The subscripts have to be the smallest whole number possible. So sometimes we might have to divide by 2 to get that to work out, right? So if you had, um, you know, I think of lead 2 oxides, we have Pb +2 and O -2. For that, they just cancel out to give us 1 to 1. So when we write our subscripts, we want to make sure that we have the lowest possible multiples. All right. Charges on ions not included in the finished formula unit of a substance. So if you have a polyatomic, for instance, you might have a charge that's going to go on the outside. Right. So charges on ions not included in finished formula unit of substance. So when I go to write this out, if I don't have that polyatomic, whoops. I'm already in pen mode here, I think, yeah. So if, what this is telling us is if I'm going to write sodium chloride, right, I don't want to leave it this way. So I don't want to write these charges out here. Now, if I have a polyatomic, though, then sometimes you'll see that. So like if I take, say, sodium and then we'll take a carbonate, CO3. So this whole thing is still a -1. And this is sodium carbonate. It can move as a unit. All right, but I think they're talking about this. They don't want us writing the +1 and the -1 on the outside here. They want us to finish that off and say it's sodium chloride, right? No charges on it. All right, now if there's no subscript, then it's a 1 implied, right? So I'm not going to crisscross my 1's down and then leave them there. All right, let's see. So determine ionic formulas. The formula of an ionic compound formed when magnesium reacts with the oxygen. So we have Mg is group 2A. It forms a +2 charge. Oxygen is 6A, forms a -2 charge. To get electrically neutral particle, then we're going to need a 1 to 1 ratio. That means my formula then should be MgO. All right, pretty straightforward, I hope. If it's not straightforward, sometimes we can use what's called the crisscross rule. So we're going to make magnitude of charge on one ion into subscript of the other. So in other words, what is the formula of ionic compound formed between aluminum and oxygen? All right, so now what I'm going to do is I'm going to get my 2 charges. So I know aluminum is a +3, oxygen's a -2. And now I'm going to omit the charges. I just want to look at the value of the number. I'm going to take the 3, I'm going to cross it down to the oxygen, and then I'm going to take the 2 and cross it down to the aluminum. And so the formula then becomes Al2O3. And again, if you've had chemistry before, then you're probably used to these techniques, right? If not, then we'll give it some practice. So which of the following is the correct formula for the formula unit composed of potassium and oxygen atoms? So for potassium and oxygen, so we'll go to our handy dandy periodic table. We find potassium. It's in group 1A, so we know it's a +1. Oxygen is in 6A. We've just seen that it's a -2. Now I'm going to crisscross them. So I'm going to take this 2, take it to the potassium, take this 1, take it to the oxygen. I no longer talk about charge. I now have K2O. And so therefore our answer should be C, K2O. All right. Which of the following is the correct formula for the formula unit composed of Fe3 plus and sulfide ions? And so here I'll give you a pause. Remember, you want to find your ions, get the charges, and crisscross them. And hopefully you got Fe2S3. All right. Which of the following is the correct formula for the formula unit composed of ions of magnesium and nitrogen? So once again, we're going to get our elements off our periodic table. We're going to use our group number to figure out the charge, and then we want to crisscross them. All right, so magnesium is +2, nitrogen -3. When I crisscross them, I get Mg3N2. All right, I think we'll stop the segment here, and next we'll get into the cations of our transition metals.